All right. I want to give you some supplementary information for lecture 2. Yeah. Mainly about hexadecimal numbers. Because in class, I couldn't spend much time to explain the background. So, I mentioned some properties of hexadecimal numbers, but, based on my observation, many students still couldn't quite understand this type of numbers. So here, let me just give you more background information to help you understand better. Okay, all right. So let's start with memory addresses. So we know memory addresses take the hexadecimal numbers, but how to form hexadecimal numbers. Okay, so we need to see that kind of background. First, we know memory addresses are integers. Yeah, because you want to specify memory locations, you can only use integers. You cannot use floating point number. You cannot use double, right? Must be integer. Okay, 1, 2, 3, 4. Yeah. But they are hexadecimal integers. Okay? So not our usual decimal integers. Yeah. So why is that? So we will see later. Right. We use one address example, because through this example, so then we can show all the details about hexadecimal numbers. Yeah. So this is the hexadecimal number we used in class. Okay, so let's still use this one, right? First, let's look at the number systems. Yeah. So there are several number systems people are using. Yeah. Although for most of our students, so you may not be familiar with, number systems other than the decimal systems, right? Yeah. This topic actually is covered in our Math 3000 discrete math class. Okay? So I believe most of you, actually, none of you have taken this one, right? Yeah. So, but you will take this one. Okay. So in this class, this topic will be covered in much more details. So here I just give you some basic information. First, the decimal system. So we're familiar with this one. We use 10 digits from 0 through 9. Okay. And we use base 10. Yeah. So there is a base. Yeah. For each number system, there is a base associated with it. Okay. The next one, binary system. And we use 0, 1, 2 digits. Okay. Base 2. Yeah. Next one, called octal system. Okay. So we use 0 through 7, 8 digits. And the base is 8. Okay. The fourth one is the hexadecimal system. So we use 16 digits. What are those digits? We will see it in next slide. The base is 16. Okay? All right. So next, we want to look at the digits of hexadecimal system. First, we need to understand the digits used in the hexadecimal system. Yeah. Why it is important. Yeah. Otherwise, we cannot represent it. Right? So that's the first question we need to answer. All right. So we need 16 symbols to represent these digits. Okay? One symbol for one digit. Yeah. But we want to have some easy way. Yeah. We do not want to, use a very complicated way. So the easier, the better. Okay? So what is the easiest way to get 16 different symbols in our hexadecimal system? Okay. So we want to use the existing symbols. Okay? We do not want to create new symbols. Think about it. If you want to use completely new 16 symbols, the learning curve is very steep. Okay? It takes much longer for people to learn these 16 completely new symbols. So that's not a wise idea. Okay? So the better way is like this, the easiest way. We take from 0 through 9, 10 digits, but that's not enough. We need another 6 different symbols. So we take from A through F. Okay? So English letter from A through F. Right? That's simple. That's the simplest possible way we can get 16 symbols, right? All right, yeah. So now we have 16 symbols. So we can represent the hexadecimal digits. Here, I do a chart, right? For the first 9, hexadecimal and the decimal exactly the same. So we look at the last 6 digits. The first one, A, okay? So corresponds to decimal number 10. Okay? Because decimal number 10, we need to use 2 digits, right? But in hexadecimal, just 1 digit. A is 1 digit, right? 1 symbol, 1 digit. We don't want to use 2 digits. Right? So here, that's the difference. All right. B, the next one, corresponds to 11. Okay, in hexadecimal, we still have 1 digit, but in decimal, we need 2 digits. Right? Next, C, 12. Okay, D, 13, E, 14, and F, 15. Okay, if you go to one more, we needed 2 digits for hexadecimal number. Yeah. So 1 digit hexadecimal number, we have these 16 different digits. That's all we need. Okay, so we can move to the next step. Okay? We want to use them to represent hexadecimal numbers. All right. Relationship between binary numbers and hexadecimal numbers. So their relationship very close. Okay? So we need to know that. Okay? A hexadecimal number is very close to a binary number. Okay? Because 2 to the 4th equals 16. That's the relationship. Okay? What does this mean? Okay? 2 to the 4th, this expression, how special? This expression, 2 to the 4th equals 16. I gave you in class. Okay? I wrote this on the whiteboard, but still, many students couldn't understand what exact meaning it is. So here, let me explain a little more. Okay? This means if we use binary digits to represent a hexadecimal digit, right? Yeah, we can use binary digit to represent hexadecimal digit. We need 4 binary digits to represent 1 hexadecimal digit. 4, okay? Why 4? Because 2 to the 4th. That means we need 4 binary digits. Here, binary digits mean bits. Yeah, bits. Yeah. So bits is coined from binary digits. Okay, B-I-T. So binary digits coined from that 2 words. All right. Next, I want to use this chart to explain how do we assign bits, 4 bits numbers to hexadecimal numbers. Okay, all right, so let's start one by one. Okay. 0 The binary representation, we need 4 bits, so 4 zeros. Okay. Next one, 1. So we just add 1 on top of the 0, so we get 0, 0, 0, 1. 2, let's add 1 more on top of the previous one. This time we have a carry at the second position, so that's 0, 0, 1, 0. Right? So next one, 3, we add 1 more to the previous binary number, so we have 0, 0, 1, 1. Okay? Next one, 4, we add another 1 to the previous binary number, but this time we will have 2 carries. The first one at the second position, but another carry occurs, so move to third position. So we get 0, 1, 0, 0. Okay? So next one, add 1 more to the previous binary number, 0, 1, 0, 1. Next one, add another 1, we have 0, 1, 1, 0. Okay? 7, we add 1 more to the previous binary number, 0, 1, 1, 1. Okay? 8, add another 1, this time we have 3 carries. Okay? So we have 1, 0, 0, 0. Okay? Number 9, add another 1. Okay? 1, 0, 0, 1. A, add another 1, 1, 0, 1, 0. Okay? B, add another 1, 1, 0, 1, 1. Okay? C, 12, add another 1 to the previous binary representation, that's 1, 1, 0, 0. D, add another 1, 1, 1, 0, 1. Okay. E, 1, 1, 1, 0. F, 1, 1, 1, 1. Okay? So now you can see that's all the possible cases that we can represent using 4 bits. Okay? Covering all the possible cases. Okay? So that's the reason, that's what I said in class, why each hexadecimal digit is equivalent to 4 bits, half byte. Okay? So when I ask you to do the calculation, so many students, felt not quite familiar with this kind of conversion. Okay? So now, after this table, so I feel you can see much better. Okay. All right. So the next one, in order to get a little more understanding, we want to see hexadecimal to decimal conversion. Okay. All right. For each hexadecimal number, there is a corresponding decimal number for it. Okay. But here we want to see how to find it. Yeah. All right. Let's see one example. Let's still use our previous hexadecimal number. Okay. Here, there are 6 hexadecimal digits. Yeah. In order to calculate its decimal number equivalent, we want to understand a little more starting from a decimal number. Okay? Start with our experience in decimal numbers. We are very familiar with decimal numbers, so we start from there. Okay? Given a decimal number, here I use a simple number, 75841. Okay? So when I use this number, we can write this number in this way. Okay? Yeah. We call it the standard form of a number representation. Why in this way? Because in this way, you can see 1 at a single digit. Yeah, so we just use 1. 4 at a 10th digit, we need to use it to multiply 10. Okay? 8 at 100th digit, we need to use 8 multiply 100 and so on. Okay? So here you can see the different digits at different positions, their contribution, their shares are different. Okay? So the digits at the lower positions contribute less. The digits at higher positions contribute more because their shares or their weights are different. Okay? And here, so the role of the base, you can see here. Okay? Yeah. So why we use base? So here, when you consider the weights, the share, you use that base and the position number to get that. Okay? So in the 10th position, we use 10. In the 100th position, we use 10 squared. Okay? And so on. Okay? So that's the way we write a standard format for a decimal number. Do we have the similar thing for the hexadecimal number? Yes, we can do the same thing for the hexadecimal number. We just make adjustments on digits and the base. Then we can figure out how large that number is. Okay, so let's start with this number. Okay, then let's do digit by digit. The contribution of the first digit, that's just 4. Okay? The contribution of the second digit, A we know equals 10 in decimal format. 10 times its base, 16 to the first power. Okay? The contribution of the next digit, A, 10 times 16 squared. Okay? Then the C contribution, 12, we know C corresponds to 12. Times 16 to the third. Then next one, 2 times 16 to the fourth. And the last one, 2 times 16 to the fifth. That's the explicit representation, the standard representation for a hexadecimal number. Okay? For this hexadecimal number. Okay? So the result is 2,028,100. Okay, so you can see. Usually we do not need this number, right? Usually why we need to know this number? Okay? In case you really need this decimal number, you can calculate. Otherwise, let's just use the hexadecimal number. Okay, all right. So that's the main background I want to give you in this supplementary material. The last thing, before I finish this video, the last thing I want to tell you is why people like to use hexadecimal number to represent addresses. Okay? So one reason. First, binary number, we know computer system use binary numbers internally, right? Internally, that's the most convenient way. Okay, but the binary number, the problem is because the number of digits is a very small number too. In order to represent a given number, you need to use many bits. Too long. Okay, so not compact, not concise. So, okay, so people want to have a more compact representation for the same binary number. Okay? Yeah. So the hexadecimal one is a very good one. Okay? Hexadecimal number, you can make a long binary representation to a much shorter hexadecimal representations, but they're still the same number. Okay? And the conversion between them also very simple. Okay? Much simpler than the conversion between hexadecimal and the decimal. Okay? All right, so that's pretty much the background I want to give you. Okay? So that should be enough for this class. All right, so I just stop here. Okay.